Hello everyone, welcome to Digital Image Processing class. So far, we have introduced several filters to remove noise in digital images. For examples, we have learned average filters, median filters, and Gaussian filters. In this video, we will introduce morphological filters and how to use morphological filters to remove noise. The idea behind using morphological filters to remove noise is the process of shrinking and growing. As you can see, the top row from the left to right depicts the shrinking process, and the bottom row from the right to left shows the growing process. In the top row, the blue circle indicates a large segment, that is, a group of pixels, and the pink circle indicates a small segment. Assume we shrink both segments at the same time. Both segments are getting smaller during the shrinking process. As you can observe from the shrinking process, the pink segment should disappear first because the size of the pink segment is smaller than that of the blue segment. In this way, we preserve the blue segment and remove the pink segment from the image. Subsequently, as depicted in the bottom row, we grow the remaining segment as shown in green so that the preserved segment is grown back by the same amount to its original size. Here, we visualize the shrinking and growing process at pixel level. If you consider a segment is an onion, shrinking can be considered as peeling off an onion layer by layer. As you can see, the top row illustrates the shrinking process. Figure A shows a segment. Figure B highlights the outer pixels of the segment, as shown in yellow. If we remove the outer pixels as peeling off an onion layer by layer, we will obtain a smaller segment as shown in figure C. Contrarily, the bottom row illustrates the growing process. Figure A shows a small segment. Figure B highlights the surrounding pixels of the segment, as shown in green. If we add the surrounding pixels as growing an onion layer by layer, we will obtain a larger segment as shown in figure C. No matter shrinking or growing operations, it is essential to identify outer pixels or surrounding pixels of a segment. To identify these pixels, we must define the pixel connectivity, that is, the neighborhood of a pixel. In digital image processing, we have two commonly used pixel connectivity definitions, including first, four-neighbor connectivity, which is also known as four-neighborhood in 4. And second, a-neighbor connectivity, which is also known as a-neighborhood in 8. Four-neighbor connectivity is defined as the 4 pixels are adjacent to a given pixel in the horizontal and vertical directions. A-neighbor connectivity is defined as the pixels contained in N4 plus the 4 adjacent pixels along the diagonals. The two diagrams on the left and right show the four-neighbor connectivity and a-neighbor connectivity, respectively. In the diagrams, green pixels indicate the neighbors of the center pixel. As you can see, in four-neighbor connectivity, only top, bottom, left, and right pixels are considered as neighbor pixels, where in a-neighbor connectivity, all A surrounding pixels are considered as neighbor pixels. In image processing, the idea of shrinking and growing process is known as erosion and dilation. And erosion is the morphological operation that corresponds to our intuitive concept of shrinking. Contrarily, a dilation is the morphological operation that corresponds to our intuitive concept of growing. In MATLAB, im_erode function and im_dilate function perform morphological erosion and dilation operations respectively. There are two input parameters of the two morphological functions. The first input parameter is a binary image, and the second input parameter is a structural element, indicating pixel connectivity. The structural element is a logical matrix where all neighbor pixels are set to true, 1, and non-neighbor pixels are set to false, 0. Thank you for watching the video. Bye-bye.